Hurrah. Okay. All right. So, whoops. Okay. So we're down to 69 graded students. 48 of whom got an A+ on the on homework 6. Good job. That was well done. The current grade distribution of class looks like this. It's a pretty normal grade distribution, with the weird exception that the biggest chunk by far are getting A+, thanks to that curve that everyone was so afraid of.
Reverse bell curve almost?
Yeah, exactly. I expect, so when's the withdrawal deadline?
31st.
The 31st. All right, so I expect that when the withdrawal deadline hits us, a large chunk of that leftmost column is going away, and then we will end up with, a interesting sort of distribution. Some statistics from there. We have one person with 110%. Actually, that's even more, because we still haven't, the bug bounty isn't included here. And that's this one person there. And I think 70% of the class is passing. Connor,
Something like that, yeah.
Awesome. Yeah. And like I said, I expect that there are a couple of people on the left side that aren't in this room. Hopefully the number is higher. We'll also, over the next couple of weeks, leave behind binary exploitation and this kind of, binary heavy security, and move on to other things that might upset this scoreboard for better or worse. We'll see what happens there. Master hackers for homework 6. This is the first 4, because otherwise, with some huge amount of people having actually solved everything, it would be forever. I got one complaint that I didn't actually read out the names last time, so here it goes. So we have Dasher, Pluto's a planet, Precitator Will, and Ponish. So good job.
I'm offended by that second name.
It's
Why is Pluto's not a planet and then become a master hacker?
That's right, exactly.
Oh,
I guess we have a bit of a meritocracy-based astronomical debate here. But I believe that next time we will have Pluto's not a planet on the top here.
that's crazy,
I'm sorry?
I think it's too many characters. We can fix that.
Yeah, I guess you can say Pluto no planet, or Pluto not planet.
No exclamation points and quiz.
Oh,
Yeah.
there you go, yeah.
Well, exclamation point will probably definitely be rejected with prejudice. Hopefully. I have to remind me that there's a critical vulnerability that we.
There are several.
Oh yeah. Anyways, there's one more that I've become aware of. Close. All right. Cool. So. I don't know if anyone has kind of hopped on recently and looked around on the previous homeworks. There's a bunch of RPI _ something people. I've invited a CTF team to play around with these, and they found some one specific bad vulnerability. Okay, cool. So, any questions for homework 6? Thoughts, debates? My original plan, of course, was to push more and more levels. Especially for that week extension, but there was just no time. I apologize. But I have a couple levels that are written, but I don't have good repeatable solutions for. If I ever get the bandwidth to finish that, I'll push it and let you guys know if you want to play around with it. Who enjoyed shell coding? All right. Who didn't enjoy shell coding? Well. Fortunately, we're moving on from shell coding. Huh?
A lot of swearing.
A lot of swearing. We are moving on from shell coding. Of course, last time that we had class, we tried to move on, and we got really stuck in a very complicated, it turned out, ROP example. We're going to push through And today we're going to talk about code reuse and beyond. So what we're going to do is have a quick recap about why we need code reuse, why we can't just have code injection, and that is the rise of non-executable memory. And we'll move on from there. Does everyone remember non-executable memory, the concept? All right, awesome. Anyone want a recap? All right, recap of non-executable memory. Basically, in the beginning, there was one set of memory, one flat memory region, like back in the 60s and 70s. If you look at ancient architectures that were extant back in the 60s or something, they would have a single end-to-end addressable memory space, and anything that ran in the computer would all share it, right? So if you had one program, however that concept existed at the time, that would write to memory space 0x8000000. We didn't have enough bits back then to even express that, but let's say memory space 0x100, and you had another program that also had a variable 0 to 100, they would interfere. And so virtual memory was created. You all know virtual memory. Every process has its own memory. And along with this, along with the management of memory separately for every process, came memory permissions, the concept of memory permissions. Memory pages could be mapped as readable, writable, as executable. So on every memory page, you can determine if the process should be able to read from that memory page, the process should be able to write to that memory page, and the process should be able to execute data in that memory page. This capability is quite old. It wasn't until relatively recently that people realized that, hey, we can actually use this to protect against things like shellcode injection on the stack, because who the fuck would need to execute shellcode on the stack, execute code on the stack? And so this idea arose about 20 years ago. It got very popularly deployed about 10 years ago, and now we cannot have easy shellcode on the stack. And we went through last time ways that you might get around this by triggering ampersand, by using just-in-time compilation that by design creates executable memory and so forth. But let's say in the general case, we need to start thinking about next steps beyond code injection. And beyond code injection, we have code reuse. The idea that, all right, maybe we can't inject our own code, but we will reuse what's there. And you've already done this using the win function, right? You were reusing the win function to get the flag in the early vulnerable levels. So there's a couple things that we can cover regarding code reuse and that we will cover. And this is a lot of material, and I've started realizing that kind of at a meta level of design of this class, I had this very exciting idea that every week we would cover a different aspect of system security. We cover it, we do a homework, and we move on. And you might have noticed that every time you ran out of time, right? And then this necessitates me writing up long tutorials and workarounds that are unfortunate but necessary this year. I think in the future, probably next time I teach this course, it'll be, if they don't kick me out, it'll be a more normal, like, single, like twice a week thing. And we'll probably have 3 classes and then a week and a half homework, something like that is what I'm thinking of. What was that?
So let's start a week and a half homework now.
So, to explore this, actually, in all seriousness, this kind of advanced exploitation scenarios that we're covering, we're going to cover them over 2 weeks. Hopefully, we'll be able to get through what we're going through this week, which is the first 3 up there. Return to libc, which is a historical curiosity, not applicable in the modern era. Return-oriented programming, which we already kind of started on. Hopefully, we can just do a quick review, and then format string abuse. And then next week we do heap, and then we're done with this advanced exploitation stuff, and we move on beyond binaries to kind of higher level security. So the homework that I'm launching this week is going to actually take us 2 weeks and count as a double homework, basically. And I will.
How does that work with the dropping the lowest homework? Because the optimizer in me says, I'm just not going to do this week's homework now. Because
Yeah, I guess we'll drop half of it. It'll count twice, basically.
Okay.
If you do bad, we'll drop one of those two. Right, I forgot to mention that. I guess you've all seen the email, but basically the idea is that to make up for the fact that we now have a few less homeworks to spread out the pain of a bad week, we're going to drop the worst homework. What's so funny? Oh, the cantaloupe?
No. What's next to it?
Oh.
I didn't have time to cook this morning.
All right. Anyways, what's up?
How many homeworks left are we going to be doing then? We got like 5 then?
Let me see what. Let's look at a calendar. When's the last day of classes? The 30th is the last day. Okay, that's what I thought. All right, so we have this double homework. Then we'll have a homework on the 7th. We'll have a homework on the 14th and a homework on the 21st. And then we will have. How does it work? Am I not allowed to assign homework after the? The final is the first week, so I would like to assign basically a take-home final homework, essentially.
So then, can we not do that given that we have drawn one homework?
Yeah.
Okay.
Yeah, you can ignore it if you're.
I was about to ask if the take-home final can count as homework that can be dropped.
Yes. It will be.
So we've got
Will the dropping of the homework impact the makeup homework that we did earlier, or does all that still play?
The dropping of the homework will be the last step taken in the calculation. So your makeup homework will be the average of the last two,
The previous two of that makeup.
the previous two, or whatever you got on that one, whichever is the highest. And then we will, after that, drop the lowest one.
We'll release Python code that shows you your grade.
Yes. And let's release it this week. We'll release it this week so you can
Or I can
model
build it
it.
into the network app.
You can do all the game theoretical models and determine how to move forward. So,
just like post it next to our name so we know everyone's there.
The issue is
what's up?
people's names change.
Yeah, but we'll send it out to your emails.
Oh, that'll work. Yeah, let's do that.
Yeah. So okay. So we have basically we have this homework, and then we have one. We have another one on the 7th, one on the 14th, one on the 21st, and the final will be assigned on the 28th. It's a take-home final that is due on whenever the final slot of this class is. It's a take-home, and it will be dropped as the lowest of your assignments if it is that. Okay. Further questions?
So does that mean we don't have to show up during finals week to this class?
I'm not showing up. You don't have to show up either. Yeah. Like for the final slot, right? Yeah.
Do you have any plans regarding Thanksgiving?
Uh,
Oh, yeah.
that's the week before class ends.
We all get together for Thanksgiving time.
I feel like you should just let us, or just 21st should be the last. Yeah. Be like a double homework or something.
That's true.
Last week's take-home final. Call
We could do the same sort of thing as now. Have a more kind of granular, a double 2-week homework.
But then we would have still have to do that homework.
Yeah.
Like solving that.
Yes.
The plan is to not do the last week's homework right now. For most of us, I'm sure.
The finals homework.
Yeah.
Then probably we shouldn't have the double week homework at the end.
I think the
Right, exactly. That's what I'm thinking. That's why it's a take-home final.
Maybe just like last homework, sign on 14th.
Last homework assigned on the 14th, due on the 30th.
Make it count as the final.
Okay. Give me a bit to consider this. We'll work out several scenarios. We also need to game theorize this from our perspective. Cool. Any other questions? Someone emailed me at some point about a couple of logistical questions like this. If you're here, did I answer all of them? All right. Cool. No one knows. It's good. All right. Moving on. We'll cover a blast from the past in the form of a return to libc attack. So when non-executable stacks first started threatening to show up, threatening of their existence, people started thinking, how might our systems now secure, right? And someone worked out a pretty cool attack called return to libc. And this attack really targeted and only really worked in the old times of 32-bit x86. This is an irrelevant historical curiosity now, but it's important to know where we come from in that sense. And so the idea is that you had a vulnerable buffer.
Why couldn't you Rob set up your arguments and write to libc?
Yes, that's Rob now. This attack in this form, and I'll explain why, is now isolated return to libc. Someone had this idea of, can we perform whatever actions we want to perform as an attacker without actually needing to use shellcode? And they realized this. If you have a vulnerable buffer in some vulnerable function and you overflow that vulnerable buffer, you'll begin to overwrite the saved base pointer, return address, whatever arguments to that buffer, and so on. Right? Generally speaking, you overwrite it. You overwrite the return address with the address of your shellcode on the stack, and you jump there. Of course, this all assumes a predictable location for the stack and your shellcode, but back then, this actually was explicitly the case. So, you overflow, you rewrite, you keep the saved base pointer the same, and you'll notice EBP because this is on 32-bit x86. And then one thing that I should stress more before we overflow is you notice the arguments on the stack. As you know, in 64-bit, where does the first argument go? RDI. Correct. So RDI and RSI and so on. In 32-bit x86, arguments went on the stack. There were fewer registers, maybe that's why. But for whatever reason, they went on the stack, and this made them very easy to clobber. So what you could do when you're overflowing things is overflow the return address with the address of system. Again, this is assuming full knowledge of the address space layout. And the second argument with the address of /bin/sh. This string actually exists in libc, or you can just inject it in the same way into your, as you're overflowing into your payload. When your vuln function returns, it'll return directly to system. Actually, let me fix this. I got too clever for my own good. One sec.
Isn't this also like vulnerable to the same issues that we ran into, like having stack canaries and all that? Which one was it? Where we had to overflow? It was 5, I think.
Stack canaries.
Yeah. Like,
in what way?
Like, because wouldn't the stack canary detect that you're just like overflowing that much and then abort it? Or?
Yes. If you have stack canaries, then you also have to get around the stack canary. Okay. So right now, this is an attack as of 1997. right? So this was well before we had stack canaries and so forth. This is no longer relevant. I'm just showing it to you as a historical curiosity.
And just something to note, stack canaries are not default, by the way. Like, you have to put a flag for a stack canary. If you compile a normal thing, it will NX your stack. You can't execute your stack by default. It's GCC. But stack canary specifically, you need a special flag for that. It's not default. It's like NX was like 10 years ago.
No, stack canaries are default now. Yeah, yeah, absolutely.
So just, is that like a recent thing though? Or like,
As of GCC on Ubuntu 18.04.
Yep.
oh wow, so super recent.
I don't know if they're on.
I think it's been a while now.
You
Hold
have
on.
to specifically turn them off.
Yes, exactly. Hold on.
Windows, they're broken with GCC, so compiling it is fucked. It tries to read a segment register and it doesn't work. Something got moved around in the latest GCC.
Oh, really?
Windows build and
Oh, for Windows.
had me pull my hair out.
Interesting.
Yeah.
All right, hold on.
Don't get on that side. Don't think wrong. Whatever.
Hold on.
How is this different from return-oriented programming
It is a special case of return-oriented programming.
for days?
Yeah, yeah, that's exactly what it is. Let me just. All right, so I had to fix one thing I just noticed. All right, so when you're overwriting, you have the return, the address of system. When the thing returns, we have padded with some fake return address that doesn't matter, that the system now thinks is the address of the function that called it. And then we have the argument to system on the stack because this is 32-bit x86. And everything works great. What we are calling here is system bin sh. Let me fix that as well. Obviously, I should be more careful with this. All right, so system bin sh. This is great, and this simply allows us, without shellcode, to call a arbitrary functions. It doesn't have to be bin sh, but arbitrary functions with arbitrary arguments. But system bin sh is generally what we want to do. The other nice thing is, with this fake return address from system, we can chain calls. So this will first put the word pwned, and we'll then call system with the argument bin sh. And so that's pretty cool. We can start, do arbitrary things. But again, generally speaking, all we really want to do is call system. But this gives us a interesting other primitive. Return to libc was discovered in 1997 by Solar Designer. His actual name is, I think, Alex something. Russian dude, responsible for a lot of cool exploitation primitives and even some security concepts, privilege separation and certain programs and so forth. And he wrote up a long email to a security list saying, hey guys, I have this really cool idea. Later on, this really cool idea was generalized into ROP. But first, let's take a look at how this attack works on 32-bit. Do we have time? Yeah, I think we're still doing good. So, wait, here's my class time here. So first of all, I've disabled, no I haven't. I'll disable ASLR. So now I've disabled ASLR for this session. So you can see the addresses aren't changing as I do LDD over and over. So ASLR is disabled. Everything's going to stay in the same spot so that we can actually do this attack. And then we're going to create a quick program that has a buffer. And allows us to overflow this buffer. And then returns. Cool? And as I mentioned, this is only applicable for 32-bit x86. So now we can run this. It just returns. If we give it enough, it'll segfault. Oh, there's your canary by default, Zach.
2014.
Dash F, no stack protector. Again, we're living in the past. So red to libc. Here's our segmentation fault. This should be crashing at 6161 something. Cool. So here we have a standard buffer overflow, but we don't have an executable stack. So if we do our standard check sec, there's no canary, but NX is enabled. The stack is not executable. So we can't inject shellcode. What we can do is do the return to libc. So we can just very quickly break at main, run. The main executable is position independent. Doesn't really matter for us because we're going to be returning into libc, and there's no SLR. We do get the address of system. It's right here. Here's the first line of system that sets up the stack. And everyone recognizes ESP as the stack pointer and so forth, right? Just 32-bit, E instead of R, extended instead of really extended. And what's it extended from? SP, exactly. The 16-bit stack pointer of bygone era. So, let's roll with this. So here we have the address of system. So we will just do let's create a Pwn Tools thing. All right, so launch the process, which is ret to libc, and we will send the address of system just like, I don't know, 20 times and see what happens. All right. Here for the log is our exploit. And let's run it. Switching to interactive mode. It's segfaulted. And where did it segfault? Add some other instruction pointer. This is the typical live demo thing when you assume that things are trivial. All right, let's just say payload is, but don't worry, we're not going to waste our entire time on this. We write the payload. Here's our payload. Awesome. So you can see it's little endian, address of libc over and over and over. So if we gdb our program and run with this payload. And then everything crashes because, oh, and we're in system, actually. Everything crashed, and we are in system. How exciting is that? Who's excited? All right, awesome. So we might have crashed for a,
Sorry, I just want to clarify. So system is what is system exactly here? It's another executable, or?
system is a library function of libc
Right.
that executes a shell command.
And that's the
And so when we run system bin sh, it'll give us a shell. It's a win condition, basically. It allows us to then execute whatever we want to execute.
Oh, because you're in. Okay.
Yeah.
it's trying to dereference the pointer to system as a string. Is that correct?
Yes, exactly. Yeah. It's actually worse than that. It seems to be. I seem to have clobbered the stack itself with system. I don't quite understand how.
Is there a leave where they're at? Like if you're clobbering the base pointer, which then is popped to the stack.
Yeah, but this function uses the base pointer.
Is it possible that it returns successfully once and then that sets the?
Oh, I think you are correct.
Yeah, because it has.
It probably tries to run something crazy, and then it, yeah, okay. So, what we think is happening is the first system runs successfully with an argument of the address of system. It dereferences that as a string, tries to launch some garbage, and then goes from there. So let's see if this is the case. We'll strace it under the use of our payload. I don't know. Doesn't seem to be the case. All right, let's GDB it. Here we go. We're stepping through. Boom, 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 boom. We're about to call gets. All right, our stack is now completely screwed. Oh, I see what happened. No, I don't. So we went straight from GDB to system. We
From gets, yeah.
from gets to system.
I wonder if that's just GDB or.
Let's do something that's not gets. Gets was a little clever, but let's do something more reasonable. So we'll read into the buffer.
What if gets sets the when gets tries to return, it's returning to?
But gets should be,
Should have its own stack.
yeah, it should have its own stack to the left of main stack, right?
Yeah.
That's what I can do. Let's remove gets from the equation. It's another, that it was cute. We were using an obsoleted function in an obsoleted attack scenario. Let's do this normal thing. Boom. Awesome.
Gets has its own stack.
It
Continuously.
Is that what you said?
it should have its own stack frame.
A stack frame?
Yeah,
Okay.
yeah.
I thought you meant
Yeah.
entirely different stack.
No, that would be cool. All right, so break main. Run this
Yeah.
payload. All right, we'll step through to the read. Interesting.
So what's that address? It's trying to reference that address.
Yeah, what is this address? Oops. Two 26748D. All right, let's step through it.
Maybe it's instruction at the beginning of the system, so it references the system again.
But that makes absolutely no sense. So, okay, we're gonna abort pretty shortly here. but this is just too interesting to pass up yet. All right, we step into read. Now we're going through libc here. We test a bunch of stuff. Okay. Here we go. We're in read. And then read is about to return, which is weird.
Yeah, I'm guessing you just had a GDB bug.
Yeah.
Try just breaking at like lead, mains lead.
So we agree that we didn't clobber anything yet. And we're in main. And here we go. And we didn't do anything. Yeah. But read didn't even call the system call.
I see.
Yeah, here it is. It calls the system call and then sec faults. Up to date GDB. You think these things will be easy? Yes. All right, here it is with no PIE. Stepping through. Here's our stack. About to call read. And we're dead.
Are you printing something after read? It might be a GDB error. I've had stuff like this happen.
How big are you writing? How much are you writing?
You're writing over your return address for read, right?
No, read should have its own stack frame.
Try printing something hard coded, just in case.
When read allocates the stack, it should be below the current frame. So if anything he writes is going to be above it.
To the left, to the right.
You're wrong.
Does put flush the buffer?
Yes. All right, here we go.
Yeah.
Read returns.
So I think it's just a GDB error.
Fucking GDB. Okay. But then Ltrace is also failed. But all right, all right.
Just try breaking.
Is it the length of what you're passing in? Is what when you did cone tools, how big to make it?
128. Well, no. That part is fine. Okay. So.
Try just putting a break on like the ret instruction of main or something, because maybe it could be either ptrace having weird issues with it, or it could just be GDB being GDB. Or like main plus 48.
Wow. So is the 32-bit toolchain just completely fucked now?
It seems like.
Okay, that's just pwnlib. All right, let's disable pwnlib.
Use PETA.
All right, here we go. We're gonna break here. No, it reached the end. But we didn't overwrite anything.
Well, so now the stack is pointing to.
That's
Yeah, to system. So it does leave. No, it doesn't do leave. Loads the effective address into ESP of EBP minus.
ECX, and then it sets
Yeah.
ESP from
So there's some weird. Okay, let's do this from something other than main. It'll work. Don't panic. All right. Ah? Do you see what happened? What happened?
Oh, it's the
Call system many times.
What is that? Bit of gibberish there. Like, is that the endian of the address backwards, or is that the?
No. Let's hex dump this.
Those are
Oh, that's a standard error.
those are the bytes of the instructions at system.
Exactly.
Oh.
So it says, here's sh : space, and then we have 313A2083. Remember that? Oops. What?
P system.
No, it shouldn't. It should be.
SH : space.
Yeah.
colon,
1 : space. Yes. 83EC0C8B. And here it is. 83EC0C8B. So. I'm sorry?
If you reference the instruction at that address and then
Exactly, because it takes that as the string pointer to the address, to the command that we should run, and it starts running the command. So fundamentally here, we're already executing the return into libc. Now let's just make it point to the correct thing. There are two ways to do it. One, the nice way is to find bin sh inside libc. So let's do that. The easy way to do that is,
You're on 32-bit, right?
yeah,
You just do it on the stack.
I can just do it on the stack, but we'll do it the elite way. Break main, this as system. It's somewhere. Actually, let's do this.
yeah, nice.
Yeah. Well,
That's correct.
how do we get this? No, we can't do that.
Yes.
No, I understand. Yeah, you need the address. Strings dash.
Can you print the offsets?
That's what I'm wondering.
I would just do a hex dump.
Hex dump is 16.
Grep for it.
Yeah. So we're gonna hex dump the library, grab sh, and there should be a /bin/sh somewhere.
Right there.
Here's
On this bin, yes.
bin csh. It's good enough.
And one of that.
One up is bin sh. Awesome.
That's not slash bin.
No, I understand it. This probably just got cut off. So let's hex dump the library. Less. Here it is, /bin/sh. So it is cf. Yeah. So that's as an offset from where the file was loaded. So now we look at info proc map, and then if we take the base of libc and we add and I of course close that. Here it is, cf bin sh. Are we excited yet? So now we simply put this after the we change how this works. Actually, let's just do this. So we have to put in the address of system, and then a fake return address for system to ignore, and then the address of our argument. So here we'll do AAA and pwn.p32, the address of the string.
Jan,
What's up?
are you sure you're not possibly just gonna return to AAAA or something now? Because you just did the entire thing times 20, right?
Yeah, I might. Yeah, let's see. There's 1 out of 3 chance of this succeeding, and otherwise we'll have to, yeah, so that didn't, and let's see. We return to AAA, so we were off by 4.
Times 2,
Times 2?
right?
No, we just needed to push it one more.
yeah.
Yeah. And then we, boom.
Did bin sh null terminate?
Bin sh is null terminated. No, that's not the problem. We are sending an argument of our.
If you took the A's as.
Yeah, it's taking your input. It's running. It's calling NSA.
Yeah.
But you're redirecting. So.
No. For some, it's taking the address of our.
Just GDB.
Yes. Let's see what's going on. Break main.
Passing the rest of the string to the message after the message executed. And the rest of the string has been passed to the message.
What rest of the string?
I mean the other AAA, other stuff we have.
That seems to be. Let's see what's happening. Let's trace this. Okay, something is happening here. Yep, it clones.
It's redirect. It's because you're redirected and it doesn't have a command.
Yes. You're completely right. So, let's do this. We'll write just enough of a payload so the buffer is 16.
Switch to interactive or
Yeah, all right, let's just do that. Why not? Run it from Pwn Tools. Nope. The basic problem, does everyone understand what's going on? So, we are writing, the program is reading 80 bytes. All right, 128 bytes. You agree?
Yes.
All right, cool. Program is reading 128 bytes. The payload is 244 bytes. So what happens to the remaining bytes?
Oh, they just go right through.
When sh starts up, it reads in the remaining bytes, and tries to execute them, errors out, quits out, goes back to our program, and then our program sec faults. So that's bad news. That's embarrassment on my part. So let's do.
So you say then it's forking the VNSH. So
Exactly. So
Send it like command like /flag.
absolutely. So let's do this, and then colon 128. We'll just execute it. Okay. So now du-hsb payload 128. If we run this, it does nothing and then sec faults. Why is that? Probably because we need a command, like you said. Sorry. That's our command right there. Let's cat flag. All right. Red to libc after 30 minutes.
So easy.
So easy. Okay. So, like I said, this is an obsolete thing that was very cool and fun back in the day, but now doesn't work. And why doesn't it work? Someone that's not in the first three rows. What does this rely on? Why does it rely on a 32-bit architecture? Arguments are on the stack, and we have direct control of them. And this is super powerful. From a single buffer overflow, we gain control of the return address, we gain control of the argument addresses or whatever, and we're basically all set to own the entire program. From one buffer overflow, we managed to call system. And all we really needed to overflow was 3 words: the return address, a garbage byte, and the argument to system. Cool. So, this is no longer the case, of course. And AMD 64 arguments are passed in through registers. And as we found out last time, if you remember the very long and painful Rob demo, those registers are not always trivial to set. Who here remembers that pain? All right, that's a couple of you. So maybe we probably shouldn't take the time to go through it again. But for now, let's take the time to have a quick break. Let's do 10 minutes. Then maybe we'll do 10 minutes later on. And then let's be back here at 7:10. Cool. What's up?
So when it forked the VNSH, so
Yeah.
the next in a
All right. Well, we're back. We missed a couple of minutes of the recording. That's unfortunate, but we'll persevere anyways. So, as with everything, there are complications to return-oriented programming. For one, you might run into limits of your control on the stack. You might need to have certain values on the stack in certain locations. And this might necessitate you to use different sorts of gadgets that can jump over those values. And maybe that we could do a demo on. There might be limits on the types of bytes that you can input. So, for example, if you're on 64-bit and you can't input null bytes, you won't be able to do a chain of ROP gadgets. You will just be able to do one gadget. Why is this? Why will you be able to do one? Let's go to Zach when we are desperate for an answer. Because I know you know. Why else? Who else? Connor. Not you. That Connor.
I'm honestly too focused
what is a ROP chain composed of?
Is that eruption kind of like just kind of dictating where you return to?
Correct. And so how do you dictate that? How do you dictate it in shellcode, where you return to?
Oh, man, rusty.
You overflow it, and what do you overflow it with? The address of your shellcode. Exactly. You overflow it with the address of your shellcode, and in return-oriented programming, you overflow it with a bunch of addresses of all of your little gadgets that you chain together to create your ROP chain. So if you have a bunch of gadgets, and you have a chain that specifies a bunch of gadgets, and these gadgets are addresses, what might an address look like on AMD 64? Or on the 64-bit architecture in general. So here's what an address might look like on a 32-bit architecture. So this is a full 32-bit address. F7 DB A000, and that's the base address of libc. And then whatever in libc would be some offset off of that address, right? Look at a 64-bit address. What is here that is not here? Higher order bits, and I hear whispers of zeros. There's a lot of null bytes in the most significant bits of addresses on 64 bytes. A lot. And this is a problem. If you are overflowing using something like gets or whatever else that doesn't allow null bytes, maybe there's a stir copy that you control the content of, and it gets copied over something else, and you can't write a null byte. Suddenly, you can't write those addresses, right? So are you completely screwed? Because I claim you can still write one gadget. Why is that?
We have to overwrite one return address.
Huh?
Overwrite one return address.
But if you can't write null bytes, how do you write even one return address?
You just write part of an address.
Why does that work?
Actually, the high order is 0, so it's when you in the end, it should be end of the string.
So it works because of little endian, right? As with all of our relative addressing tricks that you've done in various homeworks, it's little endian. So when you start overwriting, you're overwriting those offset bytes first, then you stop overwriting, and then you are kind of good to go. Anyways, usually, or I don't want to say usually, but often, if you have even one gadget, if you can redirect execution, you can usually weasel out a victory somehow, right? You can usually exploit the application. So, with all of this, with the power of return-oriented programming, and with workarounds for non-executable stack and so forth. If you can mention stack pivots. So, last time we used a tool called RP++, right? Does everyone remember RP++?
Yeah.
The gadget finder. So you have, let's find all unique gadgets that are, where's the maximum size? -R? Yes, -R, size 4 in libc, -F. Okay, These are all the various gadgets that we have in libc. Very cool stuff. So you can see, for example, that we have a gadget here, in fact 7 gadgets, one of which is at this address, that will zero out RAX and then return to our next gadget. Very cool stuff. So it gives us these various little things you can do. One of these things is an ability to do a number of things. So for example, there might be a gadget that will pop RSP. Let's see if there is. There is. So here we have a gadget that will pop RSP, the stack pointer, and then return. There are 307 of these gadgets. Why the fuck are there so many pop RSP and return in libc? So you understand what this does, right? It takes an address from the top of the stack, it overrides the stack pointer, the register, with that address, and now says, oh shit, this is now the stack, then it returns. So then it returns immediately. It grabs the return value off of the top of its current stack, or the return address. Does everyone raise your hand if this is not super clear? All right. Does anyone have a pen and a paper? Perfect. Thank you.
Cleaning up the stack frame?
Huh?
Just cleaning up the stack frame before returning. Is that what he's saying? Is that why there's 207?
I doubt it. I'll tell you why there's 307. 207. All right. What the hell? Okay. There we go. All right. So we have this cool piece of technology. Let's say that we have our stack, right? And somewhere on the stack is the return address. And we have a vulnerable function with an overwrite. And we overwrite just the return address. Let's say this is that case. I don't know. Maybe we can overwrite the return address and one more gadget, whatever, right? And here we have our value X that we write in. The gadget that we direct R to is pop RSP ret. There's 207 of these guys in libc, probably a lot in a lot of different things. And so what happens when this returns? This is our stack. When this returns, it will pop RSP, and then suddenly, how do we know that this is our stack? Is it like blessed somehow to be the stack? It's not, you are now the stack. Kind of, but what the reality is that we know that this is the stack because RSP points to the stack, right? By definition, whatever RSP points to is the stack. When we do push and pop, we dereference RSP and we increment or decrement it appropriately. So if we have this situation where we have a something writing to the stack pointer, suddenly when we pop RSP, we do X will go into RSP. So we do RSP equals X fundamentally. And suddenly, whatever other region that X points to at address X, that region becomes our new stack. Blessedly becomes our new stack automatically. RSP now points to this. And so now what happens when we do ret?
It's going to go to the address of X.
It doesn't go to the address of X. It'll read this, whatever is at the address of X, and it'll return there. So if we have very limited control of the stack, but we have control of a different memory region, we can say, you know what, screw this stack. We're going to make a better stack. Make our own stack.
An executable.
An executable stack maybe, or just a stack that gives us unlimited control of whatever data we need. And we will just jump onto our new stack. And our new stack's going to be a lot better.
Did you put X into RSP4 function or?
We put X, we overflowed. I mean, let's just do it. We're going to regret this in the end, but let's just do it.
Regret is fleeting.
Still got another hour and a half.
Got another hour and a half. We got this. And honestly, I did build in 2 classes into this advanced exploitation because I figured we'll encounter something we can't resist, like this.
You should make 2 different reads. One that's a safe read and one that's your 2 bytes of overwrite.
Sure. Let's do it. So, let's do this. We have our pivot.c. So we have one read on the heap. And we'll malloc a big thing. And then we will make another we'll have another buff that is unsafe, and then we will read buff, and we'll read enough to overflow plus the saved base pointer plus the saved return address plus an argument. Yes. Awesome. So, and then we will return.
You need another read.
That's right. So let's read also into our save buff. Cool. And no one caught that I forgot the file descriptor? Let's make things easy for now and not have no PIE. And we will have no stack protector.
You have ASLR off, right?
And in this shell, I have ASLR off. So I prove it to you now. These addresses remain constant. So
For ease, you might just want to print out the address that you're going to put it to.
nah, we can very easily get the address by L-tracing it. Here is the address. It's the first thing returned by malloc. All right, it's constant because there's no ASLR. So in the days before ASLR, in let's say up until 2010 or so, exploitation was literally this easy. You check what is the address going to be, and you know. And it's a beautiful thing. And we didn't have all of this complexity that we have now. Life was easier back then. All right, so we have this awesome L-trace. This is super cool. We have the address of our malloc. Now we need to do xpivot.c. xpivot.py. I guess real hackers will use .c for their. Anyways, okay. We'll launch pivot. We will send it whatever, let's say a shell, a ROP chain. Let's pretend that this is our stage 2 ROP chain, and then we'll send our stage 1. So we overflow. Then we have the base pointer that we're overriding. Let's just make sure that there is a base pointer. There is no base pointer. So oh, there is a base pointer. Oh, cool. Yeah, of course. Okay, great. There's a base pointer. All right, so and now we have our return address. So how do we know where to return? RP++ very nicely told us that there are 207 pop RSP ret gadgets at an offset of, where do they go?
No lower.
Let's just add it to the grep.
You're gonna need a space.
Yeah. Pop RSP ret. Grep's a very good program analysis tool. All right, here we go. It's right here. So how do we know where that is without ASLR? We just break main. We run, say info proc map. We have, that's the offset to that gadget, and then the base address of main. Let's see what's there. Pop RSP, followed by a ret. So why is there a pop RSP followed by a ret? Because we're about to abuse this in horrible ways. Why might you want this in reality? 207 times in libc.
Probably part of the block.
No, maybe because of STD call and CDEC call. I'm not sure which of the calling conventions have been used during the program.
I think that it's a misaligned instruction. I don't think there are so many instances of pop RSP ret in libc. But it's a 2-byte combination. You can see pop RSP is 1 byte, ret is on the next byte. This is a very easy thing to do. Here are these 2 bytes, C3, 5C. If you just have a random collection of bytes, every once in a while, 1 out of 2 to the 16 times, it'll be C3, 5C. Sorry, actually, that should be, that was Little Indian, 5C, C3. So, remember for the rest of your lives that x86 ret and ND64 ret is C3. And then you will have prosperous exploitation. But yeah, it's highly possible that it's part of some other instruction. And it just happens to show up 207 times in libc because A, libc is gigantic, and B, libc has a lot of rets anyways. There could be another instruction that happens to end in 5C and we're jumping halfway in. Cool? All right, so we have this and then plus our address of our gadget. And then plus the what it's going to pop in pop RSP. So let's see that. What was it? Where's our malloc? Boom, this. And of course, this is all still very kind of easy mode because we know all the addresses. This never happens nowadays, as I was about to tell you before we launched down this tangent. So now we have this situation. I'm going to add a pause here. Why am I doing this sleep? Exactly. To try to keep the effects of buffering at bay. So I'll send this input. So
You should do interactive so the process doesn't just kill itself instantly.
sure.
What does it have to do with buffering?
So if I do this, send, it might be combined into a single write. And the program will first read 1020. Whoops. The program will first read 1024 bytes. Then it will, in another thing, read whatever 48 bytes this is. 40 bytes.
You can just put a puts saying hash.
I can put a puts.
You're worried about all your data going into SQL.
I'm worried about all my data going in here.
You have to break it.
Huh?
Insert a new line or something.
Yeah, I mean, there's a number of ways around it. I was just being lazy.
And sleep is one of those ways.
Sleep will cause your process to yield, which, yeah. There's a lot of, like I said, buffering is one of the, yeah, it's a dark art. Anyway, so we read until save buff, and then we read until buff, and then we have we send our payload, and then we drop into an interactive shell to see what happens. One of the interesting things that you can do with with Pwn tools, by the way, is launch up a GDB shell that you can then also interact with. So here, or rather, this will launch the process in GDB, launching GDB in a different window, allowing me to interact with the process. It's super cool. Half the time it doesn't work.
It never works for me.
Well, you're about to be amazed. It didn't work.
I
Pwn
think it's
GDB.debug, you're right. Boom. We're in GDB. Hold on, let me init Pwn debug. Amazing. All right, see, we're in GDB, and then that's in the Python. So we can continue. What?
Oh, you didn't send the GDB debug any commands, so I don't think it breaks.
Yes, I don't disagree with you, but it shouldn't be a. Hold on. Let's re-enable my GDB debug because we're out of 32-bit land, and we'll never go back. Never. Continue. This is not something that we're going to debug right now. So like I said, half the time it doesn't work, but when it does work, it's really cool. So we're going to go back to... Oh, no, sorry. Hold on. Here's how we figure out how to make it work. Find when I used it in a CTF last. Ignore the swear word on my screen. No, fuck. Where is it?
Proud of you, Jan. You have PETA sessions there.
This is gonna go up with YouTube.
I know, this is great.
Don't panic. We have grep available to us. Or Slither server. GDB.debug. What the shit?
Maybe it was GDB attached instead of debug.
That's what I normally use. Or fail to use, I should say.
Oh, okay. Don't panic. Remain unpanicked.
First step.
That's right.
Use the panic.
Searching years of CTF.
Wow.
You just keep all this on your system all the time.
Yeah. Like, as you can see, it, okay, I see what's going on. Oh, fuck, I had it in IPython the whole time. All right, we're back. So here we're gonna go run, and here we do source equals x.gdb, and here it's going to work. What?
It's not
The
like
whole
keyword, I
thing
think.
should be
You just
inside.
had it
Yes.
quotes.
So the
Yeah, the source should be inside quotes.
Yes. This is what it runs in GDB.
You still have to have a break.
Hold on.
Is Dragon a CTF or is it related to your naming scheme?
It's a CTF.
Oh, okay, okay.
What's that bar on the top left
The bar in the top left.
of your Vim window? Is that a line? Is that B, W? Is that like syntax?
Oh yeah, syntax checking in Python. What the fuck? All right, guys, we're pulling the plug on GDB.
Wait, did you pass in? What's the pass in?
Just put a raw input before the first instance.
No, we're done. All right, we will run this.
No, just
At-
put raw input right after the process line, because then you can just GDB attach.
Yes, exactly.
Like you said, it doesn't work.
No, this works.
Okay.
You commented out the GDB.
Yeah. We're not doing the GDB. So we ran it. Now it's waiting for us to attach. We're going to GDB pivot. Sorry, got it. Beautiful. All right. We are flying again. Okay, cool. So what is happening here? It's about to do the first read. Let's hit enter here. We do a next instruction. What's going on?
No, you just, the program, if it worked, it just tried to pop and then execute AAA.
No.
That's right.
Because I'm single stepping the program.
Oh, I thought you hit continue.
But it did die with a sigil.
You should break at the end of main.
Here's what we're gonna do. We're gonna check pivot.c. We're gonna printf red. As much as I love these live demos, it's nearly unworkable. I could, but see, the thing is that if I ran through this, and here is boom, 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 and it's all sanitized, and you don't actually see any of the hiccups that you might hit, you sit down to do it in real life, and it's not boom, 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 boom. You start hitting hiccups. So balancing the amount of hiccups that we hit with, so obviously I think through, okay, this is what we will have as the source file that we explore and so forth. But the hiccups are important. In a lot of research, you actually find that the hiccups are where the research problems are.
Could you try to write it on your own, but then when you encounter hiccups on your own, you just make notes of them? That way you're like...
Yeah, I can try, but I mean, it's not impossible. People do live demos a lot better, obviously. Maybe it's not the right way to do it. Maybe you should just have it clean.
People usually practice live demos.
Yeah.
The ones that are successful.
Exactly. Exactly.
No, Jan's great. Whenever I do it, it fails miserably. So
I'd get too nervous to do a live demo.
All right, so let's just move on to, okay, forget this raw input. I know what's going on. It is never, the puts never, did we not ever recompile it? Why isn't it doing the puts?
Are you sure it flushes the buffer?
I'm 97% sure.
Wait, puts with a slash n.
There's no slash n.
It doesn't call puts. It didn't compile properly. God damn it. It's probably here. That's why it was hanging in GDB.
There we go.
Okay, great. So we did the attack, and let's see where we crashed. It didn't crash.
Why was it hanging in GDB?
Because Pwn Tools was waiting for safe buff to print before it sent anything, and GDB, the processing GDB, was waiting for input.
You should provide input because it's possible there's padding.
Yeah. All right. So we're trying again. So here's Python. Now we're waiting for this to hit enter. GDB pivot boom. All right.
Break at the end between.
This as main.
I feel like last time it was the opposite. It did SAS. So it's just SAS.
It depends if Pwn debug is on or off.
Does it really?
Yeah. All right. Here we go. We're at the end of main.
Yeah, there must be padding.
There must be padding.
So RVP is quadruple-A's. Oh.
But that should be correct. Because that's what we... No. Hold on. Yeah, E7960. And that's not it. Okay. Here's AAB. Okay. Yeah, we're way off.
Cyclic.
Here is where RSB is. Right here. So we're 16 off. We need to push this into here. Whatever. There's stack padding. This happens. This is actually one of those very important things to know and to see suffering with. All right, let's try this again. Boom.
Might have to change your Python program to type more.
What?
You only changed the C code. Oh, okay.
I didn't change the C program at all. Fuck. All right. Cool. So we will break at the same place in main. Continue. Enter. Boom. What the fuck?
Did the C program have enough to read?
Oh, I see what you're saying. You're saying this read. Yeah. The C program wasn't vulnerable enough, so we make it more vulnerable. Now we attach 22967. All right. Let's see if yep, break at the same place. Continue, enter. Awesome. So we are about to return to our gadget. Our gadget is pop RSP ret. Cool. And then if we look at what's after that on the stack, it is our malloc buffer. Exactly. And if you look at what's in our malloc buffer, it's our 414141. So what happens when I step one instruction? I'm at the ret right now. What's about to happen? We return. You can see it's returned to our buffer, our gadget, right? And now the gadget is about to pop RSP. So what will this accomplish? You hold off. What will happen when we pop RSP?
It'll pop whatever is on the stack into RSP, right?
Yeah, and what's on the stack is this. But what does it mean to pop into RSP? Changing the stack. Exactly. So when we step next, suddenly we have a new stack. Our stack is now 41, 41, 41, 41. And now we're about to return. So what happens when we return? We grab the return address off the stack. It's going to return not into the malloc. The malloc is our stack. When you return in main or whatever, you don't return into your stack. Normally, normal operation, right? You grab the return address off the stack, and then you jump there. So our stack pointer right now is this, our malloc guy. I mean, we've completely fucked over this program. And when we return, it's going to take the next 8 bytes from the malloc buffer, treat that as an address, and jump there. So if I step instruction, it'll now crash because it's about to return 41, 41, 41. Received signal 6segv. Ignore this. I was patching pwn debug for. So anyways, received signal 6segv because we are trying to execute 41, 41, 41.
So, you can set the return address. How do you, I guess, is that where you chain ROPs and then you have to now figure out where to set your next or like how do you control, how do you determine the return address where you can inject your shellcode or whatever you want to execute such that it jumps that new location?
What are you saying? What do we write instead of 41, 41, 41, 41?
No, so you can control the return address now. How would you then, I don't know, set the, like you can set a location, so then how do you set that location to be code that you want to execute? So, because you can control where it jumps back to, then how do you access that new location and make it something that you want to execute? I guess that's
Program and questions.
kind of.
So, for example, you might have a program that has 2 buffers. It's like enter your name, enter your password. So when you enter your name, you actually enter the list of ROP gadgets that you want to exploit. Or maybe ask you for your password and name, right? And your password comes first. So you put the ROP gadgets there. And password is actually safe. It's stored somewhere. It's not going to overwrite the return address. But it also just uses a read syscall. So it can handle nulls. Now when you do enter your name, maybe that terminates on a null. So here you can do basically just this, and it can pivot to where the password is stored, which is just your other ROP address.
So the way that you use this, the reason you do this isn't to get control of execution. You already have it. You needed control of execution even to hit this gadget, right? You're already specifying addresses to jump to. The reason that you do this is if your control isn't good enough in the sense that maybe you can only specify one gadget, or maybe you can only, maybe you can only specify, you can't specify enough on the stack to have a reasonable amount of gadgets to put together, because you need to put together a lot of these gadgets. So then you pivot the stack to something you have more control over, and go from there.
Alright, that works.
Maybe the stack is not executable, so we are just jumping to that address, and then so we are creating a new stack which is executable, and then we continue from that.
You can do that, but if you have a new stack that's executable, just return there, and you know where it is, right? Just
So what
return
about
their
to
shell
have
code.
different kind of gadgets over the
If you have a executable section in memory that you control the contents of, and that you know the address of, you should not be robbing. You should just jump there.
Oh, but consider our buffer is like short, somehow. And then we are going to other
It
buffers.
takes a lot less space to make shellcode than to make a rob chain. Anyways, so this is a stack pivot. And now, did you have a question?
Did you say we could do this in Win64? Given that the malloc, could we override the malloc and then on the heap?
Yeah. Yeah, you can override it. It's still not executable. But now you have a different, fully controlled area that you can, for example, have a longer rob chain in. I mean, this has inspired me. I will add a homework challenge to for you guys to do this. It's fun stuff. So you can all thank Zach. All right. The point is, though, even with that, with all of our rob tricks, we still needed to know the addresses, right? We just did an L trace, but
Sorry, is there some tool that automates building these rob chains for you? If I just type in assembly, it just goes out and finds every instruction.
there are approaches that you can type assembly and it'll find instructions. I don't think many of them are the prototypes to implement that general compilation. Like you take some shell code and it automatically chunks it up into rob gadgets. There's nothing stable that does it. There is something that builds rob chains given a goal. So let me show it to you.
So I know of two that are decent, but they do different things. One will try to execute shellcode, but one will try to give you the shellcode that you request, or an equivalent, but one you give like an abstract definition to. I think I sent you that paper, right? Or not the paper, not Anger. There is something for it that you just basically you give it a very high level abstract thing like exec VESH or just get me a shell and it will try to do it for you.
Yeah. So check this out.
Give me 3 Bitcoin.
Exactly. So you have some of you are familiar with Anger from trying to automate reverse engineering, and you know that typically if you are using Anger, things have already gone horribly wrong. But if you open up a program in Anger, and actually bin bash is quite optimistic. It's a very large program. What's something smaller than bash but still reasonable size? It's too small. Not enough gadgets. Let's do ls. So you open up ls, and now we can
Auto-load libs is true. Do you need the libs in this case? Because you want them, right?
Let's start without that. That gets very hairy. Okay, so we run an automated analysis to find all of the gadgets. And so ls is like 1/10, was it the size of bash?
And how much time did you spend on that bar there?
The bar is actually a library called progress bar. And ngraph, I didn't personally write this. It's an implemented analysis on top of Anger. Things are slowing down. That's not very good. ETA 45 seconds seems to be a lie.
Windows time.
Exactly.
So what is it doing right now?
So what it's doing right now is something similar to what RP++ does, right? RP++ goes through and figures out at every offset what is the instruction here, right? And so you've seen it here. This is from a couple classes ago where we did the same in libc, right? So it goes through at every offset, and it says, okay, if I start executing here, these are the instructions I'll execute. ngrop does something more. It also tries to understand what will these instructions do if they are executed, right? So it says, okay, this instruction will read something from the stack. This instruction will increment a pointer, and so on.
Does RGB take care about like the recursive disassembling to find if it's the correct sort of the bytes, or it just take care of the opcode? If this opcode is related to return, so just put it as
RP++ or ngrop?
no
RP++, I don't know. ngrop does. ngrop understands what are the side effects of these instructions and so forth. So now it found all the gadgets. So we can actually list them out. There's a lot of them. For every gadget, we can get its address. We can get what memory it'll read. We can get what registers it'll have control over. What the fuck is this gadget?
Can you return the block?
Here it is. It doesn't say. Okay, so it is a memory add gadget that depends on RAX. Let's see. Do we have G dot? I mean, obviously there's a way to. Does it change the stack at all? Oh, it changes the stack. It's probably a push. Push RAX probably. Or no, that's possible. Anyways. The point is, now that we have here, we can say, okay, let's exec v bin sh. And it's Python 3 now, so everything is difficult. And it crashes. Don't worry, this crashes unfortunately bad. Okay, let's say we do syscall. So what syscall can we do? I don't know, whatever. We'll call a read. Can we do an arbitrary syscall? No suitable gadgets found. Okay. Can we do system? No. The fuck? Oh, write to mem. Write to mem is good. So let's say we want to write something to a memory location using some registers, say memory, or using some gadgets, and we write hello, and it's going to give us a wrap chain that will accomplish this. Chain dot payload print payload code, and here it is. So if you wanted to write to the string hello to 41, 41, 41, we have this offset in the binary in ls, and of course ls is a position dependent executable, so we need to know the base address before we can proceed here. This is a gadget will do pop RDI and ret. It'll pop 414111 into RDI. So you notice this isn't 414141. It's 414111, and it'll become apparent why. There's another gadget that pops something into RDX, and it pops our string. Here's HELLO. And then there's a third gadget that moves to RDI plus OX30. So that's why RDI was not 414141. And it'll move RDX into it. And so it can automatically create these gadgets. This exec VE thing is really neat when it works, but yeah, unfortunately, there is something in ngrop. It's missing a try except, like one try except, and I don't know if I want to make you sit here while I fix this bug, so I'm not going to. But anyways, so that's one tool that does it. For example, ngrop is a pretty hacky thing, but it works surprisingly well a lot of the time. 60% of the time, it kind of halfway works. All right. Anyways,
I think the code is 70% of the time 100% accurate.
exactly.
Wrong burgundy.
So that was the question about automatic wrap. Anyways, back to reality. ASLR makes this very complicated. So all this time, this entire class, we've been doing this awesome thing where we just disable ASLR. In the real world, you don't get to do that, right? The core idea is that behind ASLR, the rise of ASLR is the less an attacker knows, especially when the attacker needs to be bit perfect in their exploitation, the better. And so we took away the attacker's ability to know where anything is in memory. That's pretty bad news. I was going to have a demo on how you can leak ASLR on a foraging service. Does everyone remember, I think it was the DOS binary where it would keep the same canary, and you leak that out byte by byte?
Yes.
That's exactly how. If you have a network service that forks off a new process every time you connect, the canaries will not change, the memory locations will not change, and you can byte by byte leak them and carry out your exploitation. We're not going to do a demo because we are, of course, going to run out of time. But in general, even though there are corner cases where you can work around it, ASLR is an amazing mitigation. So NX came out and it was heralded as this awesome thing, and really it didn't really do much, right? It just forced people to switch from shellcode to ROM. And that's not hard. We saw that we have tools that can do it automatically. We have tools that will give us all the ROM gadgets. It's a tedious step of, for an experienced person, a half hour or so, maybe less, but it's not a fundamental addition of complexity. But ASLR is. ASLR, most of the time, will require you to have two vulnerabilities. One which tells you where something is in memory, and one which allows you to actually use that information. Sometimes you can use the same vulnerability in two different contexts, and we'll dive into one of these primitives right now. But in general, it raised the bar a lot. Another very successful thing in the same vein has been the stack canary. Stack canary is extremely effective in what it sets out to do, which is protect the saved base pointer and the return address. So what do they share in common?
Randomness.
Yeah, randomness. The less an attacker knows, again, the better. And so then we have a question of, what if the attacker knows nothing? What if the attacker doesn't even know the actual code? And we didn't make it to this last time, right? Last time when we talked about ROB. The concept of blind return-oriented programming. So if you don't even have the program you're trying to attack, we have a remote server that we can connect to. And I'm definitely not going to demo this, but maybe we will see this again. The blind ROB attack is interesting. If you have a remote server that has a buffer overflow, you can overflow the buffer byte by byte to leak out the canary. You can do the same thing to leak out the return address, right? So now you know where the main binary is. And you can do, once you know where the main binary is, you can start redirecting execution. So when you're overriding the return address, you redirect it to different places until you get a survival signal. So what does that mean? That means instead of crashing immediately, obviously if you redirect it somewhere random, the program will crash. If you redirect it somewhere that, for example, for whatever reason calls sleep, or calls read to read more input, or calls write to give you some output, suddenly you have a signal. Either the remote connection hangs instead of closing because the server died, or it prints something out. And suddenly you know that, okay, that address is a survivable address, right? That there's something at this address that causes the program not to crash. and then you start executing ROP chains with that address as the last gadget. And so suddenly you can find other things that allow the program not to crash. Based on different effects, you can determine what these gadgets might be. There are a lot of very common combinations of hold on. There's very common gadgets in programs. So let's look at, for example, gadgets in libc. Or not libc, in bash. And you can see there's a lot of 1, 2, and so forth, but we can grab for double digits, or let's do triple digit. There's a lot of common combinations. This 241, that pop RBP, pop R12. If pop R12 is all over the place. It's a caller saved, frequently used thing. This combination of gadgets, actually, this is an interesting one. This is partway through a gadget. It's not partway through an instruction. It's misaligned. If we do 5, we should see. Oh, yeah, here it is. If you pop RSP pop, this instruction is everywhere. So in a lot of cases, you'll be able to measure effects of these instructions based on how they impact the survivability signal to try to find and fingerprint specific instructions in memory. And eventually you find enough instructions that if your survivability signal is a write, you get some output from the program. You can actually target that write at the program itself so that it writes the actual code out to you. You recall the code, and now you have all of the information. Did that make a tiny bit of sense to anybody? It's a very advanced technique, but it's very cool. So.
Has anyone worked towards automating this?
Yes. So Andrea Vital automated this in 2014. There's a public implementation of this on the internet that actually can attack an actual server. I think it was, I want to say it was Nginx configured as a forking instead of a threading server. The paper is really cool. The presentation of this paper was awesome. This guy presented it like a rock star. The tool is cool. The concept is awesome. And it's all good. Unfortunately, Andrea died in a motorcycle accident last year. So that's kind of a downer. But the work was great. So I wanted to point that out before moving on to kind of less complex ways to leak information. Right? So this is kind of the hacking blind is a crazy awesome way of leaking information, but it's overkill in most ways, in most situations. Oftentimes you can leak out things in an easier way. There's a lot of kind of ad hoc what's up?
Just performance vulnerabilities. Do you know if %n is still in the standard even past the 11?
I don't know past. If you use GCC right now with the default arguments on Ubuntu 18.04, %n is still there.
Really?
Mm-hmm. Yeah, and I don't think it'll be around for much longer. But given that it's there, I'm going to talk about it today, actually. Leaks, memory disclosures. Do you remember in your shellcoding challenge, which would say that, haha, the secret shellcode buffer at blah, blah, blah is unknown to you? This stuff happens a depressing amount, where a program will actually leak addresses to you willingly. Examples are, let's say you are in a Python sandbox and you're running code and you have class A. Yeah, if you ID A, this is a valid address in Python in the Python process. So let's pgraph Python. Ah, fuck. Let's find the correct one. This probably, nope, that one's very old. This one, 815, yes. So if we cat proc boom maps, and we see where the heap is, Python is very complex, as you can see. The heap is from 40 to 40100, and if you look here, it's not on the heap. They might have also fixed this since for Python 3.
No, it's on the 6. Is that the heap? It says the heap's 602.
You're right. Yeah. From 602, the heap's huge. Wow. All right. Yes, and that is on the heap. So that's in the middle of that toward the end of that region, and you can see just within Python, for no apparent reason, Python gives you a leak of an actual memory address. Now, if you had a memory corruption bug in Python and you were able to trigger the execution of Python, just using ID, you can leak the location of almost everything relevant, which is kind of depressing. But is the reality in a lot of programs. Other programs that are a little more careful, you can still get through by overriding the terminating null byte if there's a off by one write. And if you override the terminating null byte, we had a challenge like this, right? Yeah, if you override a terminating null byte and then trigger a print, as you know, it'll keep printing past the end of the buffer. And you can leak addresses that way. There are often logic errors, and this is still, again, situational in a program that leads the program to interpret data in the wrong way. So it has some class in memory that's one struct, it interprets it in a different struct, causing some output to you that it does not expect. We won't have a demo because we're quickly running out of time. And
Use after freeze.
huh?
Use after freeze and not initial.
Yeah, exactly. There's a whole bunch of ways that leaks happen. The one we're going to look at today that also will allow memory control is format string vulnerabilities. Format string vulnerabilities occur when you just pass unsanitized input into printf. How many people here have done this? Exactly, I've done it too. Some of my early programs when I was a wee lad were like this. And let's see what happens. I'll give you a quick preview. Actually, let's do it here. Okay, we gcc -o print.c. Let's actually include it this time because it's a variadic function. All right. So you'll notice format is not a string literal and has no format arguments. Why would you care? It hints that there is a security implication, but this happens a lot. So if you launch print ASDF, you see it prints ASDF without a new line. We can add a new line there by doing this. There is ASDF new line. Why do I have to put a $sign here?
Otherwise it'll just invoke the command instead of submitting a new line as part of it.
No, so if I just do this, it'll just actually literally input \n. \n is parsed into new line during compilation. So otherwise, if outside of compilation you have a printf and you give it \n, it'll just type \n. This is a bash shorthand that is roughly the equivalent of echo-e that, which will actually also parse out the special characters. So ASDF, very cool stuff. Some weird things start to happen. I'm gonna give you guys a quick preview. If we do this, we get a seg fault. All right, seg fault's always good. So, what the hell is going on when this happens? Let's look at how printf works. Printf takes a variable number of arguments, right? We can printf, we can use it in a lot of different ways. We can just pass in a static string. We can pass in a static string with a format specifier, %s, and then print something out. We can print numbers. We can print whole sets of numbers, floating points, and so forth. And the point is that printf adapts to this pretty readily. So how does printf know the number of arguments? And it knows because it parses the format string. Unfortunately, printf doesn't know the number of arguments from compilation or something, because then we wouldn't have an issue. Printf literally parses a string to figure out how many arguments it should access from the stack. And on top of that, as we'll get to soon, printf is actually one of the few functions nowadays that actually still takes arguments on the stack. Variadic functions in general, functions that take variable number arguments, do that. So what happens when you use printf with an incorrect number of arguments, this hello %s? Or what happens when you printf some user input? Before we get to that, we have to we know how printf learns the number of arguments, right? It parses the format string for %. But how does printf figure out where to get those arguments from? When you say %d, how does printf know where to get it from? It depends a little bit on how you compiled it. So if you hadn't included stdio.h, it actually wouldn't know that printf is a variable length function, or variable variadic function, and then it would pass it arguments on registers, and there are backwards compatibility measures to deal with that. It's not a big deal. But the bottom line is, no matter what, it'll get some of its arguments off of the stack. If you're using it correctly and you include everything correctly, and your compiler knows all about printf, it will get all of its arguments off the stack. And the cool thing is that this means that when you do printf %x, or does everyone know what %x does in a format string? Does everyone know what %d does in a format string? Yes. Yeah, %d is a number. Where the fuck did that number come from? And why does it keep changing?
It's a backslash.
It's not the /n. We can remove the /n. The number is still there and still changing.
It's the return address. ASLR.
Yeah, let's check this out. We get a trusty Python shell. We hex this. Okay, that's some weird address. Hex that. Or maybe an address. Might not be an address. But it ends in 8. That's interesting. Hex this. Also ends in 8. But we should end it with... What? Oh, yeah. It's a negative number in 2's complement, right? Ends in an 8. The fact that they all end in 8 is kind of suspicious, to be honest with you. Might be an address. Let's actually do it in our shell where we disabled randomness. Always the same. That's suspicious. See what this is. Good call. Sorry. %d, because that's what we were doing. Yeah, negative something something. And well, obviously you saw what it is in hex, so that's not a surprise.
Yeah, I said ASLR.
Yeah. So anyways, it's always the same without ASLR, and it's always different with ASLR. and it's some weird thing that always ends with an 8. It's probably some sort of an offset, probably a stack offset, to be honest. Or a stack pointer. Why are we printing a stack pointer? Why, oh why, oh why? And we can see what's going on pretty easily here.
Should it not be the return address to where printf should go back to?
No. It'll be where it expects the first argument to the format string to be.
Ah, yes, you're right. Yes. Carved outside.
Yeah. So check this out. Let's do our GDB dive into printf. Break at main, or into this print guy. We'll run it with %x. Anyways, as you figured out, %x is like %d, but it prints in hexadecimal, which is more useful for looking at addresses, obviously. So let's walk the stack up, or walk the execution up until we're about to call printf. And here we call printf with our argv1, which is %x. And printf now expects, it looks at %x and says, oh, hey, you're giving me one argument. So I'm just going to trust that you took care of everything and you put an argument on the stack for me. And what's on the stack right now? Look familiar? It's something. I don't know what this is. Is this it's just some random pointer somewhere else on the stack. Just happens to be on the stack there.
The reference for us, so it's the whole.
It's I did the XS. It's not. I mean, it's just something, right?
Because it's an address, and this address also, it's like a pointer to a pointer.
It's a pointer to a point. Yeah, it's probably the return
It's
RBP.
It's the.
Space pointer.
Yeah. It's,
NV, no.
no, it's not that.
RV,
It's not.
it's RV.
It could be argv. Let's see.
RV0. Yes.
Yep, it's argv0. Cool. So argv0 is there, and now we have this %x, and printf's going to say, I trust you. You're a good programmer. I'm just going to print out one argument. Not going to hurt anybody. And so this is on the stack, and when we next instruction and scroll up, I didn't flush. So if you continue, there it is. So why is it only printing out half of it? That's an annoying thing. We'll get to that. But now that we have the demo, actually, let's see what happens when I put %x. Nothing wrong with that in printf, right? So let's run %x, and yep. So we go next, and let's wind up to our printf, %x. Look at what's on RSP. So we have this, and then this, the bunch of zeros and a 2. If we hit continue, we see that it prints out this guy with the F3E, this thing, and then it prints out something else.
It's argv.
Yeah, yeah. This is argv. This is argc.
And NP,
And %x will print out.
What's argc? Why is it 2 in the middle?
It's probably this part of it is argc. I honestly don't know how the memory alignment works for argc. It's possible it's packed all the way, that it's 2 packed ints instead of a long. Anyways, this is honestly not as expected. So let's do %x, and let's step up to printf. Here's RSP right now. And now we hit continue. Aha. And so you can see we're printing out this guy, the 3.8, blah, blah, blah. Honestly, I have no idea why this shows up instead of 2, but we're going to move on. Then we print out this guy, and then we print out F7. Also not there. Oh, no. This is a little confusing to me. I'll be completely honest with you.
One of those addresses just read.
Let's just keep printing more and more. Okay. This makes sense. Here's where our stack... Now we're printing from our stack right here. So what? Okay. So it must start printing from somewhere earlier in our stack. And eventually it starts printing. Oh!
Stack of the GDB.
No. I'll show you what it is. So here we go. We run it. We go next, next, next. Maybe I was wrong. So here, if you look at what is on the stack, we have this D3C8 that we've seen leaked 1,000 times. Then we have this guy that ends with a 0. Then we have this 555 thing. Then we have this thing. And then we have the 2. Right? Very cool stuff. If you look at what we have in RDI, RDI is the format string. RSI happens to have this pointer in it. Then we have RCX, and then we have RDX, or whichever the calling convention was. Printf is taking its first couple of arguments from the registers and then moving on to the stack. So let's look at what we printed here. D3C8, this was an RDI, RSI, sorry, the second argument to printf. The first argument was the format string. Then we have 3E0. This was in RDX, which is the third argument. Then we have 554680, which is in RCX. And then we have F7DD0D80, which should be in R12. No, or where is it? R8. What is the next one? R9, yeah, R9. So it's here. And then it starts going to the stack. Oh, yeah, R8, R9, whatever else. And then it starts going to the stack. And here is the first thing on the stack. And here's the 0, which is this guy. And here is the next thing on the stack, which is this guy, and so on. Right? So we ran into the issue that based on whatever calling convention that happened to choose. So actually, this is a demo that I did run through. And however I compiled my demo program, it was getting stuff off the stack right away. So using printf suddenly, by injecting these %x's, and having printf assume that what we meant to do was print out crap off of that we were going to push onto the stack or into registers, we can suddenly start leaking out information from the program. This is not an uncommon vulnerability, and we'll get into why, but basically printf and its family, such as fprintf, sprintf, sscanf, and so on, are used a lot. And oftentimes, the format strings themselves are constructed based on user input. And it's very easy to mess up. So, leaking memory, what can we leak with printf? A whole bunch of stuff. We can use %c to read a single character, whether off the stack or out of registers like we saw. We can use %d or %i to read an integer, %x to read an integer in hexadecimal format, and %s to read a string. But you don't just read a string from whatever the location on the stack. It'll dereference the pointer and read a string from it. So if we have print %s, it'll actually print whatever is on the stack at this location up until it hits the first null byte. It treats it as a string. We can hit %s. So now it'll try to dereference this guy as a string pointer and this guy, and so on. %s is a pretty powerful thing. It allows us to leak out memory that is pointed to by pointers on the stack. So you noticed that we were only leaking the least significant half of everything. Why is that? It's because by default, %x and its friends, %d and %i, work on an int, which is 4 bytes. On 64-bit x86, we're living in 64-bit land. Everything is 8 bytes. But %x hasn't caught up. It's stuck in the past. So here's our %x. We can do %lx to leak along. So here's the full address there. Right? So lx, this was our D3, D8. You can do %p to leak out. It'll say it's a pointer. Give me it as a pointer. This is exactly designed to produce stuff that's readable by humans because it's freaking printf. So you can do %lx, %lx. And you can even put a pound here. It'll fill it with zeros and 016. Boom. Format it all nicely for you and everything. All right. %lx again. There's this was RSI. Right? This was our DX. This was our CX. %lx. This is R8 and here's R9. And now then we start leaking stuff off the stack. So here's our address of that was the next thing on the stack. argv lx. Boom. Here's the part of argc that we didn't get before, and so on. Right. So now you're leaking longs.
So technically, when it's reading this stuff off the stack, does it put it back on the stack, or does that mean those values are
So you
now
never
off the stack?
remove something off of the stack, right? Even when you pop it, it's still there. You just copy it into a register.
Okay.
It just reads it. It doesn't even change the stack pointer. It just scrolls through the stack reading arguments. Cool. So this is cool stuff. You can also, if you don't want the full thing, you can do %hx. This is the short. And then hhx is the char. That's 1 byte, 2 bytes, 4 bytes, 8 bytes. Very cool stuff. And this is, again, this is printf. This is literally like man printf. If you do man printf, you have all, sorry, that's not the right printf. Man printf, you can scroll down and it'll tell you all about format strings. There's a lot of good information here, actually. There's some crazy stuff with format strings, some of which we're about to go into. So, %x is all great and all, but what if the thing you want to read is like 200 words down the stack? Are you going to put a bunch of %x's? You might not have that much room in your format string. Your format string might have a maximum length to it. So luckily, the glibc developers granted us an amazing gift, and it is positional parameters. And so what you can say is, give me parameter number 1. And here it is. And let's put the LX back. Give me parameter number 2. And that's number 2. Give me parameter number 3. And that's number 3. Give me parameter number 5. Parameter number 7. Here's our argc. Parameter number 70. Something, right? And I say, oh, actually, let's see that as a string. Boom, it's an environment variable. So, positional arguments. Now we're kind of cooking with gas here. we can actually control very thoroughly where printf will start reading its arguments from. Now people are getting excited. What else can we do? We're going to take actually a quick break from what else we can do, and I'll prove to you that format strings can happen in a number of ways. I already mentioned, fprintf is also vulnerable to a format string. This happens a lot. It's used for logging. And you do an fprintf, you think that there's no problem, but what you're fprintfing has a username in it, and that is user controlled, and suddenly someone makes a username with a %n or %x. Used for input and so forth. Actually, in sudo, who here knows about sudo? Sudo obviously is a very security critical program. Maybe 3 or 4 years ago, in sudo, there was a trivial format string vulnerability, triggerable by any user. Boom, exploitation of a set UID program. You know how dangerous that can be. I'm going to demonstrate one thing about dynamically generated format strings, just to show how that this does happen, that someone could be crazy enough to create a dynamically generated format string. Where did it go? This one is something that I prepared because I didn't want to write it up on the fly. I named it a.c. Pretend that we have this situation. We have a function that centers a printf, right? That does this. Yes. I'll also send all of these out, of course. Dynamic print, hello. It's centered our hello and surrounded it with number signs. So it's a section header. You say, oh, how are you? And it'll center it to 80 characters. Pretty cool, huh? That took me about 45 minutes to write. But, actually, let's do this so we don't fuck up the log. We've already fucked up the log several times. All right, anyways. Here is what it looks like, right? And there's a bunch of tricky stuff, but the bottom line is it builds a format string with your input in it. And of course, there's a slightly contrived example. There are safer ways of doing it. But it builds a format string with your input in it, and then it printfs it and uses it as a format string, not in an improper way per se. It passes other arguments to it, but it uses it in a way that is unsafe, right? And it's passing in the exact amount of parameters here to printf that its dynamically generated format string expects to be passed in. The problem is right here, inside its dynamically generated format string, right there is user input. So we have this hello. We can just as easily say %x. And it starts spewing garbage.
And then %s, %x, yeah.
What?
So if we had the %s and we put in the %x in that
Into the
place,
%s. Exactly. So actually we can trace it to see what's going on. Here's our printf. The s printf that dynamically creates a format string using this format string. This is the result. And then it's passed into printf right here to be filled out with, for example, the little bookends on each part of our title. If we put %x here, it starts fucking up. Weird stuff starts happening. We see a null here. That's super weird. We see a weird thing here. Why is this happening to us? because we suddenly started. Let's explore it. So, let's say we put XX here. And we trace that. Well, first let's execute it. Boom. You have our dynamic format string got generated that put XX in the middle with our bookend characters around it. Everything is happy. If we trace it, we can see that the format string that got generated has a %s. And I'm jumping ahead a little. I'll go over what this 39 means in a second. It has %c, which is the character, an XX, a %c, and a %39. Actually, we might as well go over this now. Who here has used? Go for it. What does it mean?
39 spaces, I assume.
It pads it to a width of 39. That's how I achieved this centering that took me 45 minutes to write. All right. So this is how the centering happens, right? It creates a format string with a bunch of stuff. And our string in the middle here. But if you replace it with %x, instead of XX, we have %x. So let's answer the question, why does weird stuff start happening? Why are we seeing garbage? Why are we seeing nils? I mean, obviously, you know why we're seeing this 23, right? Why are we seeing the 23? But someone that doesn't play CTS every weekend. What's up?
It's pretty much the same thing because your argument in there is 23, and so that gets put into the...
Exactly. Yeah. It sees this %x, and it prints the 23. If it was %d, we would see it in decimal instead of hexadecimal. But the reason that things start being really weird and we start seeing garbage is that it takes %s here, padded, prints a blank string, %c from here. This is our bookend. This is this guy right here. Then we have %x, and suddenly we've screwed up the amount of arguments that it expects versus the amount of arguments that was passed to it. Because the program is not passing an extra argument. But we are suddenly, the count is off. So this %x prints out this 23, which was supposed to be this %c. 23 is the, x23 is the ASCII value of the hash. How do we look at ASCII values? Man ASCII. Here's the hash, hex 23. Perfect. All right, so, and then we have this %c, which now prints out this garbage, but it's not supposed to be that garbage. It was supposed to be a hash character, but the hash character got printed out as a %x, and then we do a %s, and who knows where that's coming from? That's just whatever was on the stack afterwards, after the rest of this stuff. And in the same way, we can screw it up even more. We can put %x. It'll read two things and then crash. Why might it have crashed just now? Your hand switched.
You're trying to access memory on the stack that string.
Exactly. Yeah. So let's add another couple of %x. Well, let's trace it. We just tried to dereference as this final string some garbage. It didn't produce anything useful. We can GDB it, and then I will let you guys go. So if you run %x, and then break main. Run %x. So here's our printf centered. We're going to jump into printf centered. We walk through it. Does all its weird, crazy stuff. Beautiful code. I should have just broken in printf. All right. Now we're at printf. So first we're going to look at RSI. RDI is the format string. our SI is some bullshit. I compiled this, I think, without. So you remember the variadic arguments. If I didn't include printf, it won't know it's a variadic argument. No, that does make sense. This is the typical situation again. Okay, hold on. Let's look at that dynamic printf again. So the first thing it'll do. Oh, that's not good. I apologize to anyone trying to read the slog afterwards. The first thing is supposed to be a string. So it's either an RSI or it's on the stack. Oh, it's on RSI. Yeah. Okay. Okay. Yes. So here's the string in RSI. Then what's the third argument? I typed it in already, so that was a mistake on my part. I apologize. It is our awesome hash. What's the next argument? RCX. This should be another empty another character for the other part of that bookend. Boom. And what's the next argument? R8. XS, and that is our string. Okay, and now what's the next argument that it prints? R9? Is null. And what's the one after that? It's on the stack. And it is this. Yeah. So here is what we then. So when we put %x, and maybe some few people might be lost right now, but we will recapture you. When we put %x, what ends up happening is we are going to print a %s, we're going to print the %c, we're going to print the %x, a %x, a %c, and a %s. Does everyone understand why this happens? Brilliant. You guys all good? Everyone good? All right. So this %s goes to whatever's in RSI, the second argument, because the first argument's a format string. What's in RSI is this null byte. It points to a null byte. Right. Blank string. %s, success. Great. Then we have RDX. What's in RDX? And that's a %c. And RDX is this hash. Then, so that's this guy. Then this one, %x goes to RCX. It's this. That's fine too. It prints a 23. %x here goes to R8. It's this. It prints the pointer to that string. %c after that goes to R9. R9 is a null value. That's fine. It'll print a null byte. And %s after that tries to dereference this. This is not a valid address, and the program stack falls. Pretty cool, huh? All right. So we're going to stop it here since we allocated 2 classes for this. So next class, we're going to finish off format strings. Specifically, we covered leaking. We're going to cover how do you actually modify memory with format strings. And after that, we're going to go over heap metadata corruption. So the homework. I launched it tonight. The homework is going to be a combination of ROP, format strings, and heap metadata corruption. Obviously, you're not going to get far in heap metadata corruption right now. No, not yet. But we'll have, over the next 2 weeks, we'll have this homework running, and we'll combine it all into one. So you'll have 2 weeks to... About 30 levels. This time, maybe. No, I hope everyone does. It's 2 weeks.
So for printf, could you just make it safe like that one you had? If you just had it like check user input and just disallow any percentage signs?
Yes, actually, for printf that works. The better way, there's a way to write that without needing to pass user input directly into the thing, but
Okay.
yeah.
I'm just curious, or if there was some other way to like get around that by throwing something else and it just becomes a percentage sign after.